Okay, so now let's look at the leader election algorithms. So a leader is going to be kind of like a coordinator for a distributed system, interacting with all the processes and kind of facilitating something to happen, like the mutual exclusion algorithm that we saw for a centralized solution. But as I said there itself, centralized based approaches are not that preferred in a distributed system if distributed solutions are really feasible. But still, we kind of need a coordinator or a leader to control the different things going on. So it is important that a leader gets elected in a distributed system. So that's the focus of this particular video. We are going to look at some leader election algorithms. Okay. Um, the strategy behind leader election could be of two types. One is kind of what is called extreme of findings, so which means basically a process or a computer in which a process is running, having a larger ID is always preferred. So unless a process with a larger ID does not want to become the leader, it is always having the right or preference to become the leader. The other approach is kind of preference based, where we could have processes working in a group and they can vote for a particular process to become the leader. So the preference could be based on reliability of the processes or locality and other factors. Okay, so but in this particular module, we'll only focus on extrema based algorithms that basically prefer processes with the larger ID to become the leader. And now, just as a difference between the leader election mechanism and the mutual exclusion mechanism, as well as the algorithms, in terms of like high level overview of difference between them, the leader election algorithms are like this: a process uh, may yield to the other processes and execute normally as long as the leader is elected. So a process with a lower ID will not care that it could not become the leader. Whereas in the mutual exclusion problem, we have a process competing with the other processes to access a critical section. Okay. Now, the leader election algorithms are concerned with fast and successful termination of the election mechanism, so they just want to get over with it as soon as possible and elect a leader. Whereas in mutual exclusion algorithms, we do want to increase the system throughput and minimize the response time and synchronization delay and all those things, but we also want to provide safety, liveness, and fairness to all the processes and guarantee these properties. And also, the results of a leader election algorithm must be known to other processes, because every process needs to know who is the leader of the distributed system. Whereas in a mutual exclusion problem, the processes don't need to know, even if they want to execute the critical section, but they cannot get it right now. They are not interested in knowing who is currently accessing the critical section. They don't need to know about it. Okay, but they do wait to receive reply messages or kind of authorization messages from the other processes that are currently holding or deferring their request, because those processes themselves are considering themselves to have a higher priority or kind of based on the timestamps to execute the critical section. But the processes are not really concerned which particular process is currently executing the critical section. Okay. Now, some of the assumptions behind the leader election algorithms are: each process has a unique ID, and the process knows the IDs of every other process in the system, and the communication channels are reliable, and failure can happen only to a process and not to the communication channel. So, all the channels work without failure and without dropping messages. And also, this is an important assumption: a process takes a finite amount of time to handle a message. So, if you send something to a process and you wait a reply for it, that reply will come within a finite time. So, it won't take an infinite amount of time. So, if a process doesn't send a reply within a finite time after a timeout, then it means that process has crashed. Okay. So that's how we can store the kind of whether a process is alive or not. Okay. Now, in terms of topology that we use for the leader election algorithms, there are two kinds of topology that are out there. Um, a complete topology where every process is kind of connected to every other process and can communicate directly with each other within a hop, and a logical ring topology where processes are connected in a ring, so a process can communicate only with its two adjacent processes. So a message sent by a process will go to the next message in the ring and go around and come back to the sending process. So now let's look at the Bully election algorithm. We'll go through an example. So here any process can initiate the algorithm, and so basically when a process does not see any response from the current leader within a certain timeout, it thinks that leader has crashed, and it could go ahead and initiate the leader election algorithm. So in this case, like P2 once initiated, just goes ahead and sends a claim message to all the other processes that have a larger ID than P2. So it sends the claim message to P3, P4, P5, and P6, including the P6, which was the current leader that has crashed. Now, our assumption here is P3 does not want to become the leader, so it just keeps quiet. Whereas P4 and P5 want to become the leader, so they kind of silence P2 by sending a stop message, and P4 and P5 themselves generate the claim message. So P4 sends its two higher ID processes P5 and P6 a claim message, and P5 sends a claim message to P6. So now, of course, P6 will not reply anything because it has crashed, but P5 will silence P4 by sending a stop message because P5 itself is interested in becoming the leader. So after P5 sends a stop message to P4, it waits for a while, again a timeout value, and nobody will send any stop message to P5. So if P5 does not get any stop message from any other process within a timeout, then P5 thinks that every other process is fine with it becoming the leader. So P5 goes ahead and sends the claim message, the leader message that it has been elected as a leader message to every other process. Okay. So that's the Boolean election algorithm. So even if multiple processes initiate the algorithm, eventually they are going to get silenced by the higher ID processes if they wanted to become the leader. So the weakness of the algorithm is that its correctness really depends on the timeout value. So if you don't have a proper timeout, and if a process with a higher ID wants to become the leader, but it doesn't send the stop message to the lower ID process within a particular timeout, then the lower ID process could claim to become the leader. So there could be a chance that more than one process may end up becoming the leader if the message sent by the higher ID process does not reach the lower ID process within a certain time. So of course we assume a complete topology, so all processes are directly communicable. They can communicate with each other. And also in terms of the message overhead, so you see that if at the worst case, so what could happen is, say in this example itself, if P0, if basically everyone wants to become the leader, P0, P1, P2 up to P5, so P0 could initiate the claim message, so P0 sends it to all the other processes, P1 through P6, and P1 will again send to P2 to P6, and so on. So you have a kind of n times n minus 1 or 2 claim messages, because each process sends the claim message to every other process, so that itself is a kind of big O of n square. And not only that, then the higher ID process will try to silence the lower ID process by sending a stop message, and right, so you basically see that the message overhead could go all the way to big O of n square if there are n processes at worst case. Okay. So the next algorithm is a ring-based algorithm. where you have processes arranged as a ring logically. A process can communicate only with the two adjacent processes in the ring. So now let's say there is one process is P6 that has crashed, and when a process has crashed, its two adjacent processes can directly communicate with each other. So in this case, P0 and P5 can directly communicate with each other when once P6 has crashed. So now P2 initiates the leader election algorithm by sending a kind of a claim message to its adjacent process P3. So again, we'll maintain the same assumption here that P3 is not interested and P4 and P5 are interested. And even if P0 and P1 are interested, they are having a lower ID. Right? So P2 generates a claim message and sends to P3, and P3 does not want to become the leader, so it does not, even though it is eligible to insert its own ID because the claim was generated by P2 and P3 is having a larger ID than P2. But since P3 is not interested, it does not insert its own ID in the claim message and just forwards to P4. And P4 is of course interested in becoming the leader, and it has a larger ID than the initiators, so it just inserts its ID. So P4's ID is here, and it sends to P5, and P5 also wants to become the leader, so it inserts its own ID. Now when P0 gets it, it sees that the initiator, which is P2, has a larger ID, so P0, because the initiator, when P2 initiates it, it itself it means that P2 wants to become the leader. So P0 or P1, they have a lower ID. So even if they want to, they cannot become the leader because P2 wants to become the leader. So there's no point in having P0 and P1 insert their ID in the claim message. So the claim message goes around and comes back to P2. So now P2 figures out that some other processes have also expressed their interest, and it picks out the process with the largest ID in the claim message that has inserted this ID. So it's P5. So now P2 itself takes initiative and sends an announcement message that goes around the ring telling P5 is chosen as the leader. Okay. Now, you may wonder what would happen if, say, P4 or P5 have generated a claim message, and that is also going around the ring. So what will happen is when P5 say has generated a claim message and it is going around the ring, and P2's claim message reaches P5, P5 will simply suppress the claim message of P2. So again, the idea is, so if a process with a higher ID has already generated a claim message that is going around the ring, and that process gets the other claim message generated by a lower ID process, the higher ID process will simply suppress the claim message of the lower ID process, because the lower ID process first of all cannot become the leader if the higher ID process wants to become the leader. Okay. So the strength of the ring-based algorithm is, in terms of message complexity, you have the claim message going around the ring across all the edges of the ring, and it will be suppressed at the higher ID process if the higher ID process has already generated the message. So it is a kind of theta of n complexity if you have n edges in the ring. And in terms of the correctness, it is guaranteed to be correct because a lower ID process cannot claim once a higher ID process has initiated the claim message, as well as a higher ID process suppresses the lower claim of the lower ID process. So when a process gets back the claim message, it means either it has been elected as the leader if no other process has inserted its ID, or if some other process has inserted its ID, then it chooses the largest ID among those processes and sends out the leader announcement message. So either way, we are guaranteed to find the leader, and there will be only one leader in the ring. So that proves the correctness. So if P3, P4, P5, none of them wanted to become the leader, that leader claim message will still go around the ring and come back to P2, and P2 sees nobody else has inserted their ID in the claim message, so it itself elects as the leader and sends around the announcement message. But in this case, P4 and P5 have expressed their interest, so the leader, the initiator, which is P2, has to choose the largest ID among them and announce P5 as the leader of the ring. Okay.